Hello everybody. Today we'll be doing a small video on angular momentum. Angular momentum is very similar to linear momentum that you have already done in linear motion. So let's get going. So starting with what is the definition of angular momentum. So angular momentum, and let's just try to relate it to what you've done in linear momentum. Linear momentum was when you said that mass times velocity is linear momentum. So now what do you replace mass with in rotational motion? In rotational motion, the mass is replaced with moment of inertia. Okay, so denoted by L. Angular momentum is denoted by L. So I'm just going to write here, in linear motion, linear momentum is mass times velocity. In angular momentum, your angular momentum is given by I, because mass is replaced by moment of inertia, and V is replaced by angular velocity. That's it. So concept wise, it is just the total motion contained in a rotating body. So if you have a body rotating, a turntable or a fan, or for that instance, let's say our Earth is rotating around its own axis. So Earth has a moment of inertia because it has mass and distribution of mass, and it has an angular velocity. So the angular momentum of Earth would be moment of inertia of Earth and angular velocity. That's it. Now, it is just like linear momentum is a vector, and it is measured in, if I write the units for moment of inertia, it is kg meters squares, and omega is radians per second. So the standard unit for angular momentum would be kg meters square per second. Now, what changes angular momentum? Who's capable of changing angular momentum? If I go back to my example of Earth, our Earth is rotating around its own axis, and it takes 24 hours almost to complete one rotation around its own axis. That means it's moving with a constant speed. So if it's moving with a constant angular speed, its angular momentum is constant. Now, how can we change the angular momentum of any body? For example, if I have a turntable and I want this turntable to move faster, I will have to apply more force, which would then produce more torque. So what changes angular momentum is torque. Now again, going to the linear motion, what changed your linear momentum was force, and your force was defined as rate of change of linear momentum. That's your Newton's second law as well. So, or mathematically, what you can do is you can write force as, if you're not writing in terms of derivatives, I can write change of momentum over a given change of time. Similarly, I can write torque as change of angular momentum over a given period of time. So then this would be Newton's second law for rotational dynamics. Now, so who is capable of changing angular momentum? That would be the torque. If there's no resultant torque, for example, on our Earth, the resultant torque is 0. The only force that's acting on our Earth is the force of Sun, the gravitational force of Sun, measurable force. Now, the gravitational force of Sun is not capable of producing a torque on our Earth, so our angular momentum is constant. Why our angular momentum is constant? Because the torque is 0. If your torque is 0, the change of angular momentum is 0. That means the angular momentum is constant. Now, if angular momentum is constant, now what is angular momentum? I times omega is constant. Now, if somehow the I changes, will the omega change? Because the product has to remain constant. So if I changes, omega changes. Okay, I'm going to give you an example. So can I write like I is the product of I and omega is constant. So can I write in case 1 should be equal to the case 2. For example, if I have two balls, okay, and they are at a distance r, and if I increase their distance from the axis of rotation, if somehow the distance from the axis of rotation is increased, what is happening to the moment of inertia? So this r has now, so r1 has now become r2. So because my moment distance from axis of rotation has changed, what does that mean? My final moment of inertia is greater than the starting moment of inertia. Now, if there is no torque acting on the system, final angular velocity would be less than the starting angular velocity. I'm going to give you some examples. Okay, let me just share. Okay, let's just see here. Okay, so if I see this, so this is what we just saw. Net external torque is equal to rate of change of angular momentum. That is the relationship between external torque. So if the net torque on a body is 0, the angular momentum remains constant. That is called conservation of angular momentum. This is what I just explained you with my own beautiful handwriting. Now, what I wanted to show you is this. Okay, now focus on this ring. Don't go anywhere else. Just focus on this ring. What's happening as the distance from the point of rotation, now this is the point of rotation, okay, so as it is coming closer to the point of rotation, moment of inertia, what's happening to moment of inertia? It is decreasing because it is coming closer to the axis of rotation. I is decreasing, so omega increases because there is no torque, external torque acting on the system. Another example, okay, see this one. So now this person here, this is the body mass. So if I take the axis of rotation passing through the center of mass, this has a larger I because the distribution of mass here and here is away from axis of rotation, so it has larger I. Now what it does is when it takes a jump, it brings all the mass closer to the axis. So it's bringing it closer to the axis. So what happens to the I? It decreases because the mass distribution has changed. It has come closer to the axis. So the omega increases. Now, so what it does here now at this point, it spreads his body. Why has he spread the body? Because to increase the I, and then omega decreases because it wants to land with a small speed, so the less angular velocity can be achieved by just distributing the mass through his body. Okay, another example, see a diver, a high diver. So here, as the diver starts his motion, okay, go ahead, you explain what's going to happen here, what's happening here in terms of I and omega. Pause my video and try to explain it yourself. Okay, so what is happening here is, here it has a large I because the mass is away from the axis of rotation and hence less omega. Here the diver brings all of his body mass closer to the axis of rotation, so the I decreases, and because the product has to remain same, omega increases. And the minute it wants to land, it again increases its I by spreading the mass, and then omega decreases. These are the few examples which generally you hear in your A-level exams questions. Now, so this is what's happening. Now see this one. See, what the skater does is it is trying to bring the mass very, very closer to the body when it wants to increase the speed. So he brings the limbs closer to the body and decreases I, and omega increases. Now, one of the exam questions would be something like this. Okay, pause the video, try to answer this in 3 points. What is happening to the speed of the gymnast by when she's bringing all her limbs together? So now explain the effect. So first point, let's just see. Point number 1, as she brings the limbs closer to her chest, I decreases because mass is now distributed closer. Okay, mass is distributed closer to the axis. Okay, distributed closer to axis of rotation. So we got this one. So I has decreased. So first point. So we have explained the I has decreased. Why has I decreased? Because the mass is closer to the axis of rotation. Point number 2. Now, because there's no external torque acting, okay, external torque is 0. Okay, external torque is 0. Therefore, angular momentum remains constant. Okay, so the angular momentum is constant. Fine, we got it. So if angular momentum remains constant as, so third point, I decreases, omega increases. That's it. Okay, so you have explained the effects on the angular speed. The angular velocity has increased. Why? Because I has decreased. Why has I decreased? Because she has brought the mass closer to the axis of rotation. And why the product should remain constant? Because external torque is 0. Okay, now, okay, we have done this. Now, trying to link it to something new called angular impulse. Now, if you remember from linear motion, your force was change of momentum over change of time. So I could write force times time is change of linear momentum. From similar concept, would I get torque times time would be change of angular momentum. And this quantity is called angular impulse. Now, one would think, oh my God, so many physical quantities. Why are we defining another quantity for change in angular momentum? The simple reason is sometimes the torque is changing. So if there's a changing torque for a very small duration of time, large torque or a changing torque for a small duration of time, we just calculate angular impulse. If you're not interested in that detail, just know that angular impulse is equal to change in angular momentum. That is what angular impulse does, changes angular momentum. So if I go back to my previous slide, so what's happening? Is angular momentum changing here? If angular momentum is not changing, that means the angular momentum is 0. So my angular impulse is 0. So whenever there is no change of angular momentum, the angular impulse is 0. So angular impulse is defined as the measure of change in angular momentum. So the unit for angular impulse then so just plugging in the values of torque and okay, so if I'm just going to write the unit of angular momentum would then be plugging in the value of torque. Torque is Newton meter, and then times time is Newton meter second. But if you want in more standard unit like kilograms, meters, then let's go via delta L. So this is your angular momentum is, if you remember, mass times velocity. This is how I would like to remember mass times velocity, but then remembering mass in rotational motion is inertia. So inertia times angular velocity, and inertia is kg meter square radians per second. So just per second, kg meter square per second. So either this or this depending on what the question is asking. So just to remember, angular impulse is nothing but change in angular momentum. Angular momentum changes when there is a torque, external torque acting on the system. If there's no external torque acting on the system, angular momentum remains constant. That means the angular impulse is 0. All right, let's just try with some simple question. Exercise bike has a flywheel whose moment of inertia is 40. Okay, so I have I as 40. How big an impulse? How big an angular impulse? So this is what they want, angular impulse, to bring the rotational speed up to 0.8 revolutions per second from a standing start. Standing start means initial speed is 0. So my initial angular momentum is 0. So change of angular momentum, final minus initial. So final is I omega, initial is 0, I is 40. And then you need to convert revolutions per second to radians per second. 1 revolution is 2 pi radians. So then this becomes 40 times 0.8 times 2 pi. So that would be 8 4s are 32 times 2 pi. You can always use your calculator. 64 pi, and then going for the standard units, kg meters square per second. That's the angular impulse. As simple as that. Going step by step, any point in time if you're confused, just relate it to the linear motion. Let's try another one. A bicycle wheel which is free to rotate has a diameter of 60 centimeter. So the diameter is 60 centimeter. Radius is 30 centimeters, which is dividing by 100, 0.3 meters. Okay. Mass of 1.8 kg. Fine. 1.8 kg is initially stationary. So initial angular momentum is 0. When a person applies a tangential force to the edge, I'm just, just for the sake of explaining you. So the force is applied to the edge. It would end up rotating it because of the torque produced. So the omega, the final omega is 9 revolutions per second. So again, converting revolution to radians. What is it? Times by 2 pi. Okay, 2 pi radians per second. So that becomes 18 pi radians per second. So we got the omega. Okay, we got the I. No, we haven't got the I will be mr square for a wheel. So this is m would be 1.8, r is 0.3 squared, and then you calculate. Impulse is again angular impulse is change of angular momentum, final minus initial. Initial is 0, final is I omega minus 0. I is 1.8. You can always just use the calculator here. I'm going to just leave it like that. Times 18 pi. Remember to use the unit. Okay, I've seen most of the exam papers, and when I mark the papers, we just don't want to miss the unit. That's not the mark you want to lose in your exam. Write the unit every time. And also, it's physics, it's not maths. Every number has a significance, and how would you tell the significance if you don't tell the unit? Okay, now let's just see. A person applies the force to the wheel for 3 seconds. Brilliant. What torque was applied and what tangential force was applied? Okay, so we need to get the torque and we also need to get the force. All right, so I think for this question, we need to do the calculations for the first one. So I'm just going to get my calculator. So this one is 1.8 times 0.3 times 18. Okay. Times 18 times pi. Okay. So this is coming as, my answer is 9.16. So this is coming as 9.16, taking up to two significant figures. Sorry, not two significant figures, take it up to 2 decimal points. Although I have everything up to 1 decimal point, so I should make it up to 1 decimal. So it's 9.2, because everything in the question is up to 1 decimal point. As you can see, 2 significant digits. So my answer is also up to 2 significant digits. Now, so now to calculate the force, torque. First, I'm calculating the torque. So I got the impulse. Impulse is nothing but torque times time. Okay, so we got the impulse as 9.2 and time is 3 seconds. So if I divide 9.2 by 3, my answer is then 3.1. Okay, so I'm getting 3.05 because I'm taking the original number which I got here before I reduced it, rounded error, to get rid of my rounding error. So I got my torque as approximately 3.1 Newton meter. Okay, now once you got the force, so once you got the torque, going back to this diagram, how is the torque being produced by this force? Remember, the perpendicular distances are in this case. So I'm just using torque is equals to force times perpendicular distance. This is 3.1 perpendicular distance. So F you have to find, and the radius is 0.3. So if I'm not, to get rid of my rounding error, I'm dividing my original answer by 0.3, which would then give me 10.18, so 10.2. So just to get rid of my rounding errors, this is what I'm doing. So my force is then just doing this, so 10.2 newtons. Do you see what I did? So I got the impulse from using impulse formula. I got the formula for the value of the torque, and then I went to my original diagram. This is why drawing the diagram would help. I did not have any cognitive load in thinking, oh my god, how do I calculate torque? Just you have it in front of you. Force times distance gives you the torque. Okay, just before we end, next video I'll try and make some questions on AQA and Excel. Before now, just read through the question and then try to answer the question. Okay, now so again, pause the video and try to answer it yourself. Once you've done that, so as you can see, you have a normal star whose radius is around 700,000 kilometers, and it is making one rotation every few weeks. Now, when it is ended its life, it's started collapsing because of the gravity, and the radius is shrinking. Because the radius is shrinking, the moment of inertia, it decreases to, and because the moment of inertia has decreased and there's no external torque, its speed increases to, can you see, 30 rotations per second. With how large speed it is rotating, just to conserve angular momentum. Okay, the speed increases enormously because the radius decreases, moment of inertia decreases, distribution of mass, moment of inertia decreases. To keep angular momentum constant, conserve angular momentum, omega increases enormously. All right, so that's the end of today's video. Next video we'll do and solve some questions. Well done for learning, well done for revising. Thank you.